Hi, I'm Pavel, and I'm here to tell you about some of the work that my colleagues and I have been doing to try to build community resources and infrastructure for the numerical software and floating point community. Now, our community has been doing some incredible work over the last few years. I'm talking about work like the mechanized proofs of very tight error bounds, and the tools for automatic verification, for floating point program optimization, and even for accuracy improvement. These are all problems that a few years ago seemed incredibly difficult to make any progress on, and yet we're seeing rapid improvement. I think this is work that we as a community can be incredibly proud of. And it's for that reason that I think it's important for our community to keep on growing, to keep on tackling new and innovative problems, specializing further, and innovating more in our research methods. Now that's all great, but in order for the community to progress and to grow, it's going to have to overcome some growing pains. These are common problems that occur in many research fields as the research field itself becomes bigger and more diverse. Let me give you a few examples of what I'm thinking of. The first might be what I'd call the growing pain of composition. That is, if you've got a floating point program, you can use a tool like ROSA to check whether it achieves a given accuracy bound. And if it doesn't, then there's a different tool, like SALSA, that can improve its accuracy. This sounds great. These tools can be used in concert, except for the fact that the two tools actually require their inputs to be in slightly different formats. This means that using both means manually translating your work, which can lead to typos or other mistakes. Or if the translation's being done automatically, it means additional work for the implementer, more code to write, more formats to support. Another growing pain is what I might call the growing pain of evaluation. Our community has sometimes multiple different research approaches to a particular task. For example, fluctuate an FP-Taylor measure and try to bound the error of a floating point program. But comparing them is difficult. If you check their papers, you'll find that they were actually evaluated on different benchmark suites. And though there is cross-comparison in the FP-Taylor paper, it's hard to know that the benchmarks chosen represent the wide diversity of floating point programs. Finally, there's what you might call the growing pains of standardization. For example, both Herbie and Stoke internally use a notion of error called the units in the last place of error. But if you look at the details, you find that they compute slightly different error measures. For example, the error between nan and the infinite value is different for the two. I don't think this is an essential difference to the research approach. It's just an idiosyncratic and accidental difference the two introduced. Now, these same growing pains have appeared in many communities, compilers, SAT, and usually the solution has been to build common community infrastructure that eliminates these problems. With FPBench, that's what we're trying to do. FPBench is a project to build community infrastructure, to build common resources for our community that make it easier for research groups to cooperate and compare with each other. We're hoping that this common infrastructure makes it easier for our community to do its research, to continue specializing, tackling new and challenging ideas, and making rapid progress. I want to ask all of you to check out our website, fpbench.org. On the website, you can find a mailing list where you can lend your ideas, your criticisms, your cooperation, and also our GitHub and drafts of preliminary work. I want to tell you a bit about this preliminary work, but I do want to emphasize that the work I'm going to describe is just the start. It's just the first few bits of community infrastructure that we've started building. With your help, I hope that FPBench becomes the sort of broad community project that can be a home for community infrastructure and resources, and for all efforts to make our community easier to work in. So let me tell you about the stuff that we've started doing. These are what we felt were the issues that came up most often in our own work. The issues of having a common format to allow tools to interact, a common benchmark suite to make it easier to evaluate different tools on the same set of benchmarks, and a set of named measures to help standardize what different tools mean by floating point accuracy. So, I'd like to start with the common format. In some sense, the common format is the bedrock of the other two pieces of work that we've done. And with the common format, our goal was to find a simple to implement, but still relatively expressive format that different floating point tools could use to interoperate. So let me start with a very simple example. A straight line floating point expression, square root of x plus 1 minus square root of x. And here you can see how that expression is rendered in our common floating point format, which we call FPCore. You can see that FPCore is a simple S-expression-based language. We're hoping that it's as easy as possible to parse and to evaluate. And you can see that each benchmark carries a body expression, in this case the original floating point expression, and a collection of free parameters, which means that FPCore is able to represent library functions, not just end-to-end routines. Now, this FPCore expression is rather stark. It doesn't include a lot of information that we might want, like a description of what the program is doing, or preconditions on its parameters. In FPCore, those can be added through a metadata mechanism. So here, you can see that I've specified a name for this expression and a citation as to where I found it, which link it to the broader floating point literature. You can also see that these metadata variables don't just have to be irrelevant to the program in question. They can also be things like preconditions, which add additional information about the uses and the meaning of this program in a machine-readable form. We're hoping that these metadata fields become a key mechanism for allowing FPCore to be extended and elaborated as time goes on. Now, this is a single straight line expression, but FPCore can also handle more complex programs. For example, this program uses, I think, Newton's method to compute an approximation to pi. And you can see that in this program, we're using both common mathematical functions, like here the power function, and also loops, like here this while loop. Both of these features are supported by FPCore, and we're hoping allow FPCore to express the broad range of programs that people actually use in numerical software. So, in working on FPCore, we had three big goals that we wanted to accomplish. We wanted FPCore to be easy to use, simple. This way, researchers wouldn't be held back by having to implement it. It'd be a help, not a hindrance. Secondly, we wanted FPCore to be expressive, to be able to capture the broad range of programs that our community analyzes. And finally, it had to be extensible, something that could grow and change over time as our community did. So, in trying to make FPCore simple to use, we settled on an S-expression-based syntax, which would be easy to parse, a purely functional bottom-up evaluation strategy that would be easy to code up and to analyze, and a mechanism for loops that specified all values in single static assignment form. The hope is that the transformation to SSA can be centralized. You can generate FPCore from this higher level imperative language that we call FPIMP, or in fact, from any other language that you can write the tool for. But because FPCore programs themselves are specified in SSA form, analyses, improvement tools, and optimizers written by our community don't have to redo that analysis internally. And that's another part of making FPCore easy to use. We've also tried to make sure that FPCore is expressive. I've already mentioned that all C and Fortran standard mathematical functions are included in FPCore. So anything from POW to the Bessel functions. And also that loops and conditionals are supported by FPCore. So with these features, we've been able to express the sort of programs used in a large range of floating point research. And we're hoping you'll find the same. Now, I should add that not all tools will reasonably support all of the features of FPCore. For example, I worked on a project, Herbie, that only worked on straight line expressions, no loops. That's fine. I don't expect that every project will support every FPCore feature, but by having this common language, programs can still interoperate, at least where that makes sense. Finally, we've put some effort into making sure that FPCore is extensible. It can deal with changes in our community and adaptations to new research problems. And we've done that chiefly by focusing on these metadata properties. So I mentioned these briefly before. These are basically a way of associating structured data to an FPCore benchmark. These can be things like names or descriptions, human-readable things, or they can be things like preconditions, postconditions, and variants that are more machine-applicable. And not only is there the possibility of adding this metadata to benchmarks, but there's also the possibility of having tool-specific metadata. I'm thinking things like descriptions of how many intervals to use, or descriptions of a mode that the tool should run in. These can be part of the input to a specific tool, but can be ignored by other tools using the same benchmark. And this tool-specific metadata can also be generated by tools that use FPCore as an output format. A tool might describe additional internal information it used, or internal evaluations of error measurements. So with this extensibility, expressiveness, and most of all simplicity, we're hoping that FPCore is the sort of thing that different floating point tools can implement and then use as a common interoperable base language. So that's this common format. And once we have a common format, it becomes possible, and we've done it, to create a suite of common benchmarks. Now, I think many of you watching this video have experienced the difficulty and time that it takes to properly evaluate a software tool. And that time often comes from the difficulty of gathering a representative suite of benchmarks that can properly exercise your tool's features. I think often this difficulty is a barrier to entry to our community, and is keeping a lot of productive and important research from getting done or published as quickly as it otherwise would be. So, with FPBench, we've tried to pool together common benchmarks from different research groups. We've got 72 benchmarks right now. We're hoping to add more. And all of these are drawn from existing research projects. So they represent the sort of programs that our community is already interested in. We've annotated all of them with the source, ranges for inputs when known, descriptions when known, and citations in the literature. So we've tried to keep these benchmarks connected to the broader floating point community and work. Let me give you a bit of a numerical breakdown of what this benchmark suite looks like. As I mentioned, these benchmarks are drawn from existing research groups' suites. We've got benchmarks from FP Taylor, from Herbie, Rosa, and Salsa. And if you or your colleagues have a benchmark suite, please let me know, or the FPBench project as a whole on our mailing list. It'd be great to incorporate them into the benchmark suite, and I'm sure be of significant utility to other researchers. We've also covered the broad range of features that FPCore supports. Now, of course, yes, every benchmark uses arithmetic expressions, but we also have significant coverage of the exponential and trigonometric functions. We've also got a lot of programs using loops and branches. So this covers a lot of the features that a comprehensive floating point analysis tool would have to have. Finally, we're also starting to cover the diverse domains that numerical software comes from. A lot of these benchmarks are textbook examples, but we've also got examples of mathematical algorithms, embedded systems, and scientific computations. And again, with your help, we'd be extending all of these lists to establish a more representative and comprehensive benchmark suite. Finally, once we have this benchmark suite, it's going to become important to compare the outputs produced by different programs. And to compare those outputs, we need to standardize different measures of error. So the tools that are attempting to measure the same thing actually do measure the same thing. Now, in doing this work, it's been important to us not to restrain the research community. There's a lot of different measures of error because they're more conducive to one or another research approach. And slowing down research is the opposite of our goal. So instead of picking a single metric of error, we've chosen to standardize choices along 5 different axes of error measurement. So in each of these independent axes, we have a few stark standardized choices that you can choose between according to your research goals, the end users you're trying to cater to, and what's best for your tool. But because there are these formalizations of each of these choices, tools can still agree on what it is that they're measuring. So let me give you a rundown of these axes of measurement. The first is the choice of absolute error, relative error, ulps of error, bits of error. This choice is important and also frequently conducive to different research approaches. Now, these tell you the difference between 2 floating point numbers, a measure of the difference between 2 floating point numbers. But equally important is to know which floating point numbers you're comparing. So forward versus backward error basically asks that question. It asks, do you fix the input error and look at the corresponding output error? Or do you fix the output error and look at the corresponding input error? So this is an important choice, especially for different end-user scenarios. Whether you're talking, for example, about end-to-end error, or error between different components of a complex hybrid system. Now these two tell you about the measurement of error at a single point. But if we're comparing things like library functions or implementations of mathematical routines, it's important to aggregate this notion of error. And the 2 most common ways of doing that are maximum and average error. So these 2 give you a measure of the aggregate across all floating point numbers. But usually we can't actually test every floating point number. So there's also the important choice between using sound and statistical techniques to measure this aggregate error. Statistical techniques can be more accurate. They can give tighter error bounds. And they're often better for measuring average error at the current state of the art. But sound techniques can be better at measuring maximum error and can give strong formal guarantees about their correctness. So this is another important trade-off for tools that measure error. It wouldn't be fair, in other words, to compare a statistical and a sound error measurement tool because they're trying to achieve different things. Finally, we now see multiple tools that have to compare the accuracy of 2 different programs. For example, Salsa, which attempts to improve the accuracy of a floating point program, has to compare the accuracy of the input and the output program. And there's 2 different ways of doing that. One method is to compare the aggregate change in error. The maximum error was this much, now it's this much. The difference is the improvement. But the other way is to look point by point and aggregate afterward. So you can say, oh, the biggest improvement in error was in this many ulps. The worst unimprovement in error was this many ulps. So this is another crucial distinction. The tools that improve floating point programs or otherwise compare pairs of floating point programs have to be aware of. So we've standardized and formalized these measures of error. The hope is that tools can choose among this palette of options, but once they've made their choices, stick to implementing the standardized measures that we've described, avoiding the idiosyncratic choices, like that silly difference between Herbie and Stokes' implementation of Ulfs of error. And this should make it easier to interpret the results of tools, compare them, and have different tools interoperate. So these three things, the common format, the benchmark suite, and the formalized measures, are the things that we've started doing within FPBench. But I want to now zoom back out from the work we've started doing to the broader vision of FPBench as a project, which is that FPBench ought to be a community resource, a place where our community can build infrastructure to support ourselves and our research in this field. FPBench should be a place where we can make it easier for different research groups to cooperate and compare with each other. And the work we've started doing is only a first step toward that. If you would like to help, whether by helping us design the common format, the benchmark suite, the name measures, or by proposing new sorts of community infrastructure that our community could build to make it easier to do work, please get in touch. Join our mailing list, which you can find on fpbench.org. Look around our GitHub, the preliminary work we've started doing, our draft specifications, and let us know what you think. My hope is that FPBench stays a community project, a resource that all of our community benefits from. And to do that, ultimately, it needs your help. Thank you.